So in this lecture, we are going to talk about a state space representation. This will be just a brief introduction of state space representation, uh, although it's a very big topic, but we are just introducing this representation in this lecture. So we are currently in the modeling phase for uh, our during our study of control systems. So what we are trying to do is to find out mathematical models for various systems and processes. So one model that we have studied is the transfer function model, right? And we have seen how the transfer function model helps us in uh, representing the dynamics of systems, representing the system dynamics in a compact and convenient way, right? And from the transfer function representation, you can go to block diagram representation of multiple subsystem systems, and then we have also seen simplification of multiple subsystem systems using signal flow graphs. Uh, the state space representation is a time domain representation. The transfer function representation was a frequency domain representation. S is the frequency variable. So basically, you converted from a differential equation, a system of differential equations, to a system of algebraic equations using Laplace transformation. Now, this representation has its own advantage. There is no conversion to the frequency domain. It has its own advantages and disadvantages with reference to transfer function representation, but it is a more representation, modern representation of uh, uh, control systems, right? And it is especially useful and amenable for multiple input, multiple output systems. Right? So let us briefly see what is the general state space representation. So the general, before I introduce how it is done, so the general state space uh, representation for an LTI system. Remember, we are talking about linear time invariant systems, right, in this course. So general state space representation for an LTI system would be something like that, like this. So x dot is equal to ax plus bu, y is equal to cx plus du. Now, these look to be simple equations, but they need a little explanation. So when I put this dot on top, it means I'm talking about the derivative, so dx by dt, right? And the other thing is that these are vector equations. Vector equations. I hope you understand what vector equations mean. First thing, that this is a differential equation. It's a set of differential equations of order 1 because there is only one derivative, a single first order derivative, x dot. So, and this is an algebraic equation, right? So, and then these are vector equations. Why? Because x is actually a vector. Vector means you can understand a vector right now to mean something like which has multiple entries. So x is actually a number of variables clubbed together as a matrix, right? So x1, x2 goes up to xn. So x, we say x belongs to a real space, and it has n components, right? So why do we call it a vector? It requires some understanding of linear algebra, which we have not seen yet, but it is sufficient to right now say that x x has n components, right? So like when you write x dot is equal to ax plus bu, it actually means that if for example n is 2, right? If n is 2, that this means that x1 x2 dot is equal to a times x1 x2 plus b times, right, u. Now one or two more things in this. So basically what if you write in general the state space representation like this, you also write the order for the various uh, inputs and outputs and the state variable that you have. So this X belongs to an n-dimensional space. It has, so when I say it belongs to Rn, it means that it has n components, right? So this actually means it is understood that X would be x1, x2 going up to xn, right? Similarly, the number of inputs to the system, right? It could be a P input system, right? The number of inputs could be P. So U is not one, it's U1, U2 goes up to UP, right? Similarly, the number of outputs could be more than one. So Y could be Q1, sorry, Y1, Y2 goes up to YQ. So all of them, X, U, and Y, are not single entities, but they have n components, right? X has n components, U has p components, Y has q components. So that is why this is a system. This would be a system of n. Let me write this with a different color. N first order differential equations, right? And these are called state equation. This is called a state equation. N first order differential equation. It's called a state vector equation because X is called the state vector, right? State vector. Similarly, this would be, now how many equations would this be? Because the left hand side has q components, right? So these would be q algebraic equations, right? Q algebraic equations, and these are called output equations. So X, Y, and U have been resolved. Now let us look at A. What is A going to be? Now when you write X dot is equal to AX plus BU, you know that this vector is of size n cross 1. That means this also has to be of size n cross 1, and this also has to be of size n cross 1. And since this is X is already n cross 1, that means A has to be n cross n. So A is an n cross n matrix, right? A is a matrix, the size is n cross n. Similarly, U already, you know, U is P cross 1, and the product of B and U is n cross 1. That means B has to be, yes, it has to be n cross P, because only when you multiply n cross P with P cross 1, you'll get n cross 1. So this gives you the sizes of A and B. Similarly, you can find the size of C. So the second equation, y is equal to cx plus du, the output equation, right? So this is of size q cross 1, right? And x is of size n cross 1. So the product cx has to be of size n cross 1, q cross 1. So for this to be q cross 1, c has to be belong to q cross n, because only when you multiply q cross n with n cross 1, you'll get q cross 1. Similarly, this is p cross 1, and d has to be q cross p. So these are all matrices. These are all real matrices of different sizes. Now let me illustrate this. So you could have something like, say, if you have a single input, single output system, that means P is equal to 1, Q is equal to 1, and suppose the system is of order 2, that means N is equal to 2, then you would have something like this. As an illustration, x1, x2, right, would be equal to, say, 1, 5, minus 3, 2. This is your A matrix, x1, x2, plus, since this is n cross n, right, and your B is n cross P, so your B would be, say, 2, 4 times u. U is a scalar because it's a single input system. So this is 1, 2 cross 2, and this is 2 cross 1, right? And similarly, your output is a scalar. Output would be Cx. C, C is would be Q cross N. Q is 1, so it has to be 1 cross 2. So minus 1, 4, for example. I'm just writing it like that. So this is 1 cross 2. That is Q cross N, x1, x2, plus D is a scalar because it's 1 cross 1. Q is 1, P is 1, plus 5U. So this would be a state-space representation for a system. Now you can instantly see the advantage of representing something like this. The biggest advantage that you can see very clearly is that you can represent a multiple input, multiple output system, or a single input, single output system in the same basic formulation. The basic formulation being this. This is not true for state space representation, because the state space representation that we have seen, the transfer function is, we have seen the transfer function ys by us, or cs by rs, where c was the output. So single input, single output systems, we have seen the transfer function representation. But for multiple input, multiple output system, you'll need to have transfer functions between all the inputs and all the outputs, right? So you will not have a single transfer function for MIMO systems, because the transfer function is the ratio of the output by the input. So if you have two outputs and two inputs, so you have two outputs, C1s, C2s, and you have two inputs, right? R1s and R2s. Then the transfer function representation has to be, for the LTI system, has to be between these outputs and inputs. That means the transfer functions, there would be four transfer functions: C1s by R1s, right? C1s by R2s, C2s by R1s, C2s by R2s. So there would be four transfer functions for a multiple input, multiple output system. So you can instantly see the advantage of the state space representation. So I'll now explain what it is and how it is done. So before I do that, we need some definitions. So we need the definition. So without talking too much about linear algebra, we'll take some quick definitions of a number of things. So we say linear combination, right? Okay, before we say linear combination, let us talk about system variable. So when we say x is a variable, a system variable, what does it mean? All right, any variable that responds to an input or an initial condition, right, in a system is called a system variable. So if you don't like this variable being repeated, you can say any quantity. So for example, if you apply voltage to an electrical system, you'll have a number of voltages that would be changing, a number of currents, charges, right, changing within the electrical network. So you'll say all these voltages, currents, right, the charges, the fluxes, these are all system variables. And for example, you have a mechanical system, right, and you apply a torque. So the displacements, the angular velocities, right, the angular acceleration, and all these things would change. So you'll say all these are system variables, right? So a linear combination is defined as a combination of n variables. When you take n variables, a combination of n variables xi, you take them for I is equal to 1 to n, and you just multiply them with constants. So you say k1 x1 plus k2 x2 plus you go up to ki xi. So you just multiply each of the variables with constants. So ki is a constant. So you take these n variables x1 to xi and you multiply each of them with constants. Then you say that S is a linear combination. Say S is a linear combination of the variables xi. Uh, you define something called linear independence from this. Linear independence is a set of variables is said to be linearly independent, right? So a set of uh, variables. Again, these variables, system variables, is said to be linearly independent if S is equal to 0, only if, right? If and only if. If and only if all k's k1 to ki are equal to 0, right? And no xi is equal to 0, right? So, so what it actually means is that you you can combine the uh, the variables and make the linear combination equal to 0 only by taking all the constants and multiplying them with 0, right? So an example is, for example, you must have read about the I vector in vectors and the j vector, where your I vector is a unit vector along the x-axis and the j vector is a unit vector along the y-axis. So if I say that I multiply I with some constant alpha and I multiply j with some constant beta and I make the sum equal to 0, I will not be able to do this unless and until alpha is 0 and beta is 0. Both are 0 because I and j cannot cancel each other. So you'll say I and j are linearly independent vectors, right? Right? But for example, if you have I as one vector and 5i as another vector, then what you can do, you can have alpha times I plus beta times 5i equal to 0 if you say alpha is minus 5 and beta is 1, right? So here you are taking a linear combination of two vectors. One is I, the other is 5i, and you are saying that these two vectors can be combined to give a 0 vector if a certain combination of scalars is taken. So here these two vectors are linearly dependent and these two vectors are linearly independent. Okay, this is just quickly telling you what linear independence means. So now we come to state variables, right? So why did we require this definition of linear independence is because a state variable is a set of linearly independent system variables. A set of linearly independent system variables. So all the system variables you take and you from them you take out a set that is linearly independent, right? And it is such that the property is such that the values the values of the set at time t0 along with known inputs completely determines the value of all system variables for all t greater than equal to t0. So a set of linearly independent system variables such that the values of this set at time t0 along with known inputs completely determines the value of all system variables for all t greater than equal to t0. This is a slightly technical definition. Now, what is a state vector? The state vector is the vector x that we were talking about. A vector, a vector in this case means a column matrix, right? A column matrix, right? And you can understand this because you can represent I in the coordinate system as 1 0, right? And j as 0 1, right? So maybe you get you see the analogy between column matrices and vectors from the physics side as you have studied before. So a vector, right, whose elements are state variables is called a state vector. Are state variables. So in our notation, X is the state vector, right? Then what is the state space? The state space is the n-dimensional space. N-dimensional space. Why is it n-dimensional? Because X has n components. So if X would have had two components, we would have said it is two-dimensional. Three components, three-dimensional. And beyond three dimensions, although we cannot visualize, but we can always put it on paper. Something having n components actually is in the n-dimensional space. So n-dimensional space whose axes are the state variables, right? So if you have, for example, in this example that we saw, you had a two-dimensional system, two vectors. So if you could plot x1 on x-axis, x1 and x2 on, say, one of them on the x-axis and the other on the y-axis, and if you could plot the values of x1 and x2, you could show the evolution of the system, the variables of the system in a two-dimensional space. So this space would be called the state space, right? And then we have the state equations. The definition of state equations we have already seen. These are n first order differential equations, and the output equations are q algebraic equations, where n is the number of state variables, p is the number of input variables, and q is the number of output variables. So this is very briefly about state space representation. Now let us come quickly to some examples where we could actually write down the state space representation, right? We'll take up circuits only, although we can easily extend this to mechanical systems that we have seen, but for this lecture I'll be confining myself to only circuits, right? So let us take a simple circuit. uh, Say suppose you have a series RLC circuit, right? A series RLC circuit, which we took in the beginning also when we talked about the transfer function representation. So if you want to write down the differential equation for this, Vt is equal to, this is, we always start from the modeling from the first principles. So the first principles in this case are the KVL and KCL. So 1 by C integral I dt. Now, instead of writing this differential equation, we can write an integral differential equation for this, right? So instead of writing this integral differential equation, sorry, the other way around, we write the differential equation. So we can write dVt by dt is equal to R dit by dt plus L d square it by dt square plus it by c. So this is the representation, differential equation representation of the circuit that we have presently. But we want the representation that we can cast in this form: x dot is equal to ax plus bu, y is equal to cx plus du. We want to identify the state variables, the inputs, the outputs, and then put them in this form and say what is the value of a, b, c, and d. Now, how do we do it for circuits? For circuits, remember that state variables, the state variable vector is a spatial vector. What is special about this? There could be many system variables, right? Current is a system variable. The voltage across this resistor is a system variable because this changes with change in input. The voltage across the inductor could be a system variable. The voltage across the capacitor is a system variable, right? Similarly, the magnetic flux inside the inductor, is a system variable. It changes with change in input. The charge on the capacitor is a system variable. So there are many system variables, but the state variable vector x is special. What is special about x? X would be linearly independent system variables, and they are such that if you know them at time t is equal to 0 and you know the inputs beyond time t is equal to 0, you know everything about the system. So it has to be something special. So there is a thumb rule for selecting, without going into the details, there is some thumb rule for selecting state variables in circuits. So what we do, we take the inductor voltage, sorry, inductor current as one of the state variables, and the capacitor voltage as the other state variables, right? So this current IT, because this is the current flowing through the inductor, is the state variable, and this voltage VCT is the state variable. So the state variable vector is defined, right? According to the thumb rule, we have to select it like this. X would be VCI, VCT, IT. Now we have to find these two equations. The equation that will have x dot, right? And we have to find this x dot would be VC dot and I dot, and we have to find it from the basic differential equation that is given here, right? So let us look at this differential equation again and see whether we can, do something about it. So we have this. Remember, we need to have x dot on the left half side, right? So we have the differential of the current here, the derivative of the current, and on the right half we have x, so we can have I, and we have inputs. Now what do we do to this integral term here that we have? So instead of writing it like this, we can rewrite it like this. So we write Vt is equal to Rit plus L dit by dt plus Vct. We write it like the capacitor voltage, because capacitor voltage features in our state variable representation as it is a state variable, right? Now we can take the derivative term to the left hand side, and we can write dit by dt is equal to minus Vc by L, right, minus R by L, VCT by L, sorry, minus R by L IT plus VT by L. So I've taken these two terms to the left hand side, right, and divided by L throughout to get this equation. Now this is my one of my state variables, right, current being differentiated, and on the right hand side we have a linear combination of the state variables VCT and IT and the input. So this equation is one of the state equations, this one corresponding to the state variable below. The other equation that I require is derivative of VC. Now if you see VC, C dVC by dt, right, is the current of the flowing through the capacitor, right? I is equal to C dV by dt, right? The capacitor current is given by this equation. So that means if I can write CVC dot is equal to IT, I can write VC dot is equal to 1 by C IT. So this is the other state equation that I was looking for. If I want to put these two equations together, I'll be writing VC dot is equal to 1 by C, sorry, is equal to 0 times IT plus 1 by, sorry, VC dot is equal to 1 by C times IT. Just a second, I have put VC dot ahead of this, so it is going to be equal to 0 times VC plus 1 by C IT, and similarly IT dot is equal to minus 1 by L VC plus, sorry, minus R by L IT plus 1 by L VT. Now look at these two equations. Aren't these your state equations? Yes, they are. So you could write something like this: Vc dot t, I dot t, right? Although it's difficult to put a second dot over I, is equal to 0, 1 by c minus 1 by L minus R by L VCT IT plus 0, 1 by L V of t. Right? So this is the state equation for this circuit. So these are your state variables. X dot is equal to, this is your A matrix, this is your X, plus this is your B matrix, and this is your input. X dot is equal to AX plus B. You can have an output equation for this. Suppose any one of the system variables here is the output variable. Suppose the in resistor voltage is the output variable. So VRT. So VRT. Now we have to express the output in terms of the state variables. The state variables are current and voltage. So it is 0 times Vc plus R times IT, right? So the output equation VRT is equal to 0 R VCT IT plus 0 VTs, because there is no D term here. So this is your output equation. Y is equal to C X plus this 0 is D and this is U. So you have the state variable representation for the system, in which you have basically represented the system dynamics in terms of two variables: the capacitor voltage and the inductor current. Now what is special about this representation is that if you know the values of Vc and I at some time t0, and you know the input that you're applying from 0 to from t0 to t, then you can find out, because of the state variable representation, every system variable, right? Every system variable, the value of that variable from any time from t0 to t. And why is that? It is because these two variables are linearly independent variables, and since it's a second order system, it's a second order differential equation, so it's a second order system. See, the differential equation is a second order, so it's a second order system. So there would be at most two linearly independent variables in the system, and these two variables are sufficient to know everything about the system. So in general, the order of the differential equation, right? Order of the differential equation, which is actually governing the system, or you can say the order of the denominator, right, in the transfer function representation, right? This is equal to the number of state variables. And if you identify the state variables correctly and you write down the state space representation, that is sufficient to know everything about every other variable in the system. So this was whatever I had to tell you about the state space representation. You'll have to do a couple of more examples to understand how to apply this to more complicated circuits than this. Thank you very much for listening.